the right side I have opened the paper, the research paper which you have sent to me. Here are the result of the deflection, vertical strain and the radial strain for different value of subgrade modulus. Look at this. Here the fiber content is 0%, 1%, 2%, 3%, 4% when the fiber length is 10 mm and the material type is PE. So for this type of material, by changing the fiber content, the subgrade modulus will change. So that's why for every fiber content we have used different MR values, subgrade modulus values. We can also see the subgrade modulus values here in the table above, that is table number 5. For the fiber content 0%, the resilient modulus value of PE at different ratios for 1 centimeter length we have 140. So it means that we have take the subgrade modulus of subgrade is equal to 140, that is the resilient modulus value will be 140 for the fiber content of 0%, and for 1% we will take 145.2, and for 2% we will take the resilient modulus 147.9, and for 3% and 4% this value is 148, 171. So these are the values for 1 centimeter length when the material is PE. Again, if we go to see the table, similarly the table 6 is for the fiber having length 2 centimeter. So the vertical strain, deflection and the radial strain values in table number 10 have been found for table number 5 and table number 6, fiber which the fiber content they have added, and the type of material in table 5 and table number 6 is PE. So the strain values has only find out for this table number 5 and 6. So for this we have to open the Keenpave software. This is the Keenpave software. By opening this, we have to click on the layer input, and then we have to put the layers properties. That is, first of all we have to go and click on file and then click on new, and then go to the general tab, and general tab we have to write the name, any name you can give to this problem. So let's say X3, and then go to the type of material. Here in the paper they use the linear type of material, so we will put here for linear is equal to 1, and then they need no damage analysis, so we will put 0 for no damage analysis. And then the number of periods per year. Here you can see that in table number 10 look at the fiber content. By changing the fiber content, we will the subgrade modulus resilient modulus value will change. So how many times the subgrade resilient modulus will change, we will find out from this. See, it's 0, that is the 1 subgrade modulus resilient modulus for 0% fiber content, and then 2 subgrade resilient modulus of subgrade for the fiber content of 2%, and then resilient modulus for the fiber content of 2%, and then resilient modulus of subgrade for the fiber content of 3% and then 4%. So if we calculate these, then we will come to know that how many times this resilient modulus of subgrade will change. So 1 2 3 4 5 1 2 3 4 5 6 7 8 9 and 10. So there will be the number of periods. We will write here 10 1 0. After that, the number of load group, we will take it 1, because in your paper they just use a pressure, single pressure. So the load group type we will take is 1. And then the tolerance for numerical integration, its value is 0.001 by default, and it is the tolerance which you have to be consider while doing analysis through this software. So by default it is 0.001. And then after this you have to put the number of layers. So look at the table number 9. We have one layer is the asphalt concrete layer, the second one is the unbound granular layer, and the third one is subgrade layer. So there are 3 layers, so we will put here 3 by default. There is 3 written here, so no need to change, as already 3 here it is written. And then the number of z coordinates for analysis. And now look at the table number 10. In table number 10, we have seen that the vertical coordinate z value for a single resilient modulus of subgrade, we have 3 values. That is the vertical coordinates. It's mean that they want to know the deflection, the vertical strain and the radial strain at a depth of 0.000 mm, and then 10 mm, and after that 30 mm. So there are 3 points, vertical points at which they need the deflection. So we will just write here 3. And then it's the numerical integration. Again, how many times the software have to do the integration to find out the results. So it depends on you whether you increase or decrease the result will according to the number of iterations the software has been done. And then the type of response, if you want result only the displacement result, I mean that you need just this row, this column, so you have just type 1 here. But if you don't need only displacement or deflections, then you will press 5 plus traces. You will I mean that if you just write here 5, then in result you will only see the displacement plus traces. But if you write here 9, then you will see all kind of stresses, displacement and strain. So you will, in the result you will find these 3 things: displacement plus stress plus strain. So I need almost all these values, so that's why I am using here 9. By default 9 is already written here. And then all layer interfaces bounded. So again, in your paper no discussion about the bound, so there's by default it have been taken 1, so we will use 1. And then the number of layers of bottom tension and number of layers of top, by default it has been 1, so leave this as it is. And then the system of units, if we see here the units are in mm, that's mean that we have to find the result in mm. So for this we do not use the English units, but we will use here SI units. So we will change this, go to 1 for SI and then click OK. After the general we will go to the Z coordinates. So in Z coordinates we have for each resilient modulus of subgrade we have 3 points at which we want the deflections and strain values. So for this we have to write the vertical coordinate depth. So here the depth is 0, so we will write 0 and then click. the value, when you just enter the value, it goes from left to right. It means that the software take your values, and here we do not enter value yet, so that's why it's on the left side. Again we will put here value, that is a vertical coordinate at 10 mm. So the 10 mm is equal to 1 centimeter. So in software we will have written only 1 and then press enter. After that we have here 30.001, so it means that it's equal to 1 centimeter, sorry, 30 millimeter is equal to 3 centimeter. So here in software we will write 3 and then enter and then OK. After this we will go to layer, click on the layer, and then in layer we will go to give the thickness in centimeters of each layer, and then for the last layer we consider it as infinite thickness, that is subgrade, so we do not need to enter or put value for the subgrade. And this is the Poisson ratio values. So look at this in the paper. There are 3 layers. For the first layer, that is asphalt concrete, whose thickness is 0.10 meter. So it's mean we have to write this value in centimeter. So 0.1 meter is equal to actually 10 centimeter. So we just write 10 and then press enter. Similarly, the thickness of the unbound granular is 0.20 meters. So converting these 0.20 meter to centimeter, we will have 20 centimeter thickness for unbound granular, and press enter. And then go to the Poisson ratio. For the asphalt concrete we have the Poisson ratio 0.04, so we will write 0.4, press enter. And then for the unbound granular we have value of Poisson ratio 0.3, so we will put here 0.3, press enter. And then for last, for the subgrade, the Poisson ratio is 0.45, so we will write here 0.45 and then enter and then click OK. So we completed the general done, the Z coordinate done, the layer done, and leave the interface because it's for the bounded and unbounded layer, so leave this as it is, and then go directly to the moduli. In moduli we will just now put the values of the stiffness of each layer. So like it is given in this research paper here, that we have the modulus of elasticity for asphalt, that is 4000 megapascal, and then for granular layer we have 200. So it means that asphalt concrete have 4000 megapascal elasticity, and then unbound granular have 200 megapascal modulus of elasticity. So if we click on the period 1, then it needs the values of the modulus of elasticity here in kPa, but we have the values in MPa, so we will here increase the values, that is we will write 4000 megapascal, and if we want to write it in kPa, then we will add we will write 3 more zeros, so it become now in kPa. So 1 2 3 4 5 6, yeah, good, and then click OK. After that go to the layer number 2. For the layer number 2, it's the granular layer, 200 megapascal modulus of elasticity, so we will write here 200 and converting them to kPa, so we will write 3 more zeros and then it will become correct. So the last layer is the actually the resilient modulus value, which is being changing by changing the fiber content. So here we see that we have changing the fiber content how many times? 10 times. 1 2 3 4 5 6 7 8 9 10. So for the first 0% fiber content, if we go to table number 5, here table number 5, so look at this. For 0% fiber content, that is 0%, the resilient modulus value is 140 megapascal. These values are in megapascal, so here we will write 140 and writing 3 more zeros, and then it becomes in kPa. So how many zero here? 1 2 3 4. Yeah, that's right. Click OK. After clicking OK, again click here OK, and then go to period number 2. Again, by changing the fiber content percentage in the subgrade layer, it do not change the value of asphalt concrete layer as well as the granular layer. So the E values will be as it is, that is 4 0 0 0 and then 2 1 2 3 4 5, and then this value will change, the subgrade value will change. For 1% we are going now to do, we are going now for 1%, so that's why we will write the resilient modulus value of 145.2 megapascal. So here we are just changing this value to kPa, so we will write 145.200. so it is now correct, and that is now in kPa. Click OK and then OK. So we have done period 1, period 2, and then go to period number 3. For period 3, the E value for first layer will not change, that is 4 3 0 1 2 3, sorry 1 2 3, I mean that we have to write 6 zeros after 4 to change it to kPa. So here 2 1 2 3 4 5, enter, and then we will just add this value for resilient modulus of subgrade, that is 147.9. so 147 sorry 147 and then 900, enter, OK. And then period number 4, for period number 4 1 2 3 4 5 6, enter, 2 8 1 2 3 4 5, enter, and then 148 sorry 148 1 2 3 zeros, and then click OK. Period number 5, so here again write 4 1 2 3 4 5 6, and then 2 1 2 3 4 5, and then we have to write 171, so 171 and 30, it will be click enter, and then click OK. Now we have done 5 periods. For period number 6 to 10, the values in table 10 is for the PE material with the fiber length of 2 centimeters. So we will go to table number 6 and then take the values of MR from this table, this row, first row. So go to period 6 input and write again. The value will remain the same for asphalt, concrete and granular layer. That is 4 1 2 3 4 5 6, enter. 2 1 2 3 4 5, enter, and then 1 4 0 0 0 0. So okay, and then period 7 4 1 2 3 4 5 6 1 2 3 4 5, and the last one is 1 44 1 4 4 1 2 3 0. Click OK, and then period 8 1 4 7 9 0 0, enter. Okay, and then period 8 1 2 3 4 5, and then 152 1 2 3. Click OK, and then last period number 10, the value for the asphalt concrete modulus of elasticity 4 1 2 3 4 5 6, enter. 2 1 2 3 4 5, and then the last value 158 megapascal. 158, convert it to kPa, so we will write 30, we will write 30158 000, enter. Okay, again click OK. So here we just add the modulus of stiffness or modulus of elasticity. Here it is now done, and then going to load. So we will just add the load type and the load magnitude. So here we have just only load that is for the single tire. Here it's a pressure of 860 kPa, and there is a linear elastic method. We already followed this one, and the tire is the single axle single tire. So for this we will write 0 as it is, and then the contact radius. So contact radius, we have the diameter of 152 mm, circular shape of tire area. So we will just write the contact radius of 152 divided by 2, so it will equal to 76 mm. So 76 mm for contact radius we will divide the diameter by 2 and we will get 76 mm, and here we have to write in centimeters, so that's why we will write 7.6 centimeter and then click enter. So the contact pressure here is in kPa at 60, so contact pressure of tire will be at 60 kPa and then press enter. This is the values we have to write for the case of when we have dual tires or tandem axles. So for this we will write this value, but we have single load, again type 0 in both XW and YW, and then we just need only at the center of the tire, so we do not want the values at a point at a radial distance from the center point. So for this we will just write, we just need only value at the center, so we will just add 1, click OK. By clicking OK, by entering OK, by entering the value and clicking OK, this page will open. Here we have to write the radial distance, so we do not want at a distance other than the center, so that's why we just need at a center, so 0 centimeter. We will just type 0. It's okay. Go there, then click on OK. So up to this point we have done. So now go on save. So the file is being saved. We will go on exit, or we should save as, so that we can give it name x3. OK. So the file with the file name of x3 has been saved. Then click on OK, and then we have to go to exit, and then go. Our problem has now done. We have just to check the values, so go to editor and then file, click on open, and then go to Keenpave. So you can find these values by clicking PC and then go to see Keenpave, click on X3 and click open. So this text document open. Now we can see the values here. So these are the values for the vertical displacement. This displacement, these values 0.6779, 0.678, 0.4. So let's check it with the results of the paper and the vertical strain. So here these are the stress values and these are the vertical strain. Here in the bracket they write the strain just below the vertical stress. So the first value is the vertical stress and the below value is for the vertical strain when the depth of a point is at 0, and then when a depth of a point is at 1 centimeter, that is 10 mm, we will have the stress value this, and the displacement vertical strain value this much, and the deflection at point located 1 centimeter below the ground surface will be this much. And similarly 3 centimeter, that is 30 mm, the depth of the point, when the depth of point is 30 mm, the deflection will be this much, 0.472. So these values are in meter, so we have to check it with the paper, research paper, and these are the stresses, and these are the values of the vertical strain, and these are the radial stress along with the strain values below the radial stresses. So this is the radial stress value at 0 centimeter depth, and the deflection at this point, the radial strain at this point will be this much. So similarly, this is the radial strain and this is the radial strain. So now compare it with the results of the paper. Go to table number 10. Yes. So for fiber content of 0, we just use the period number 1, 0 mm, 10 mm, 30 mm. The deflection values are this. So for 0 mm we got 0.67791 meter, and here we have 0.678. so it means that they just round about the value and we get this value, and here is this much value. This value is in mm, in millimeter here, and this value is in meter, so almost equal to each other. Vertical strain values, that is minus 387 multiply 10 power minus 6 microsine for 10 power minus 6. So this is the vertical strain. So here at a depth of 0 millimeter, so we will go here for a depth of 0 mm or 0 centimeter. The deflection is this much, and the vertical strain value is 3 minus 387.4 multiply 10 power minus 5. So here is 38.74, here is 38.7. so it means that if we just move this decimal from this point to the right side of 7, then it will become 387.4, and this will become now minus 6, minus 387.4 multiply 10 power minus 5. This is the vertical strain, similar to this value. And then again for the radial strain we have 365.9 multiply 10 power minus 5. so it means that it is 365.9 multiplied by 10 power minus 6. If we just move this decimal to this point, then it will become minus 6. So 359.9, 365.9, and here is 366. So by rounding up we will become the 365.9 will become 366 multiply 10 power minus 6. so these values are equal. Similarly for these values, or these values represent the strain, vertical and radial strain at a depth of 1 centimeter or 10 mm. These are the 10 mm values. In 8.1 minus 350, this is 8.1 minus 350, the vertical strain and radial strain. So these values are equal. So okay, we have done now. Thank you.